evening. It's the 12th of April, 2020 in Honolulu, and I'm going to go over modeling the COVID-19 infected curve using log-normal distribution and utilizing the SIR model concept, which is max infected of a population is a function of R0, which is the reproduction number. Curves for USA and Hawaii will be shown at R0 equals 1.3 and compared to our initial unmitigated R0 of 2.4. Okay, the key concept that I pulled out of the SIR system of ordinary differential equations right here is this key equation that I could utilize because these equations don't settle into a explicit form as a whole, although I have this, which is the maximum infected number over the total population. So it gives you the percent of people infected as a function of R0. That's pretty key. So I went to the Wuhan study to keep it all in the same ballpark. The data, with their massive amount of data, they came up with 2.38, which we are just I'm rounding off to 2.4. And what that does is, here's 2.4, and it puts about 42% of the population will be infected at that R0. And then, like I said, we're going to get down to 1.3. So that is about 15%. That's a huge reduction. Yes, and it works out to about 1/3. Okay, the other key element, so there's the infected, but many of them will go undocumented. 86% go undocumented. So of the 44%, only 14 will be diagnosed, for instance. Or if at an R0 of 1.3, then we have 14% of 14%. Okay, here's an example of megadata. The gray cell phone is the user being tracked. Currently an undocumented, not infected individual. So passing by all these cell phones does not produce contamination. Now the next example is an undocumented infected user, first infected diagnosed person, two more infected diagnosed persons, and now an infected undocumented person who will do their own track, and the original one moves out of position. And that's what happened to 20 million cell phone accounts in China, in my opinion, locked up for megadata study, no mystery. Here's more megadata. Here's what it looks like when it starts getting really big. Spreading. Okay, so I'm going to be utilizing a log distribution, log normal distribution, and notice it's skewed. It has a steep curve on one side and a longer, slower curve on the other side. It is also not normalized like the bell curve, where you add up all the elements and they add up to 100%. In this case, that is not true, so it's not normalized. But this best matches epidemiological curves, so that's what we're using. Okay, this is the model that I created to solve basically for this product right here. Um, I'm using the Excel solver function and Excel lognorm distribution function. Those are the two key functions. Um, Real data comes in over here, the size of the population, and then one has to decide what R not to use, and that will feed the number of diagnosed. So here's a number, the number diagnosed. Another set of real data is the actual total cases that come in, and they would be recorded in this column right here against the dates. However, the log normal distribution would not be using 1, 2, 3s. It's using small fractions, so you have to create an x naught, a starting position, and then a delta x. In this case, I used large numbers, but these are actually fractions. You need a starting value because in order to better fit the curve rather than when data first became available. Um, okay, so next part here is I have the real data over here, and over here I have my model data. The model data, again, depends on, these are the 5 variables. Sorry, these are the 5 variables that control the log normal distribution, the probability density function, which will be this output right here. And then I just add them up to create the cumulative density function, which then is compared to the total right here, and right here becomes an error between column 3 and column 5 at each row element, and you add them all up and send it, well, it goes to this placeholder right here, the sum of errors between the real data and the CDF, and here's a visual of the alignment which will occur when the error is minimized. So there's 2 errors being minimized simultaneously. First, the CDF to total data over here, and then the sum of the PDFs has to match, these two have to match. So that becomes the sum of the PDFs versus the diagnosed, misspelled, sorry, diagnosed numbers right here. And so that feeds into the total error. And then this program keeps crunching away. It's a nonlinear multi-dimensional root finder until the total error, this value, goes to a minimum. And at that point it stops and you have a curve. So let's go into the curves that we generated. First, USA at an R naught of 1.3, see a peak happening on the 6th of May. That's 23 days away. At the peak will be 47,000 people infected a day. The total at the end of the wave will be 6.5 million diagnosed, and using a 3.2% CFR, which is reasonable. It's not get a death count of about 200,000, and we can compare the 1.3 R naught to the 2.4 R naught there's a big difference here and a lot of volume difference. So this works out. This curve is about 33% area under the curve smaller or size of the larger one. So we reduce the total cases to 33% by mitigating from 2.4 to 1.3. So that's awesome. In Hawaii, did the same thing at 1.3. Have a peak predicted on the 29th of May. That's 46 days away. We'll have 134 cases average at the peak, about 18,000 people diagnosed and almost 600 dead. And the curve kind of finishes, look, next year, February. Now it gets real small over here. Okay, again, we have a big difference between mitigated, the mitigated curve at 1.3 versus our other curve at 2.4. So again, this is great. Can we get it lower? Just want to note here real quick. Most of the activity, you know, New York City, New Jersey, Boston, Detroit, Chicago, Miami area, New Orleans, Houston. It's all ports. LA and Seattle area. Notice there's not a lot going on here, although it is happening, but not quite to the same intensity as these high density population centers. That unfortunately promotes the spreading. So Iowa has its peak about a month later, as an example of the Midwest, a month after the USA peaks, and you know, about 300 cases on the peak day. Washington State, on the other hand, which is only twice the population, has 4 times the size of a peak. Okay, anyway, so that's all I have. It's good to have a plan in order to see how we're progressing against this COVID-19 virus. It could be, it most likely isn't exact, or it's hard to say. We won't know until later. All right. Good night and stay safe.